So this is the first Ansys assignment. Ignore my desktop. First, you're going to go to Maxwell, and then you're going to hit Maxwell 3D. And once you're in there, you're going to want to go to the Modeler tab and click Import, and then you're going to import the file that was on Canvas. This file is in the Ansys Resources module, and then it's going to put the geometry in the project. And then you can go ahead and save the project as whatever you want to title it. I've titled it EE511. I'm not sure. It took me way too long to decide what to call it. Because I'm doing a voiceover. Alright. So I just called it EE511 DC motor assignment. Oh, EE511 DC motor sim assignment. You don't need to title it that, but that's just what I did. So then you're going to want to go to Maxwell. You're going to right click Maxwell Design, and you're going to click Convert to 2D, and you're going to choose the ZX plane to split the 3D model. And then you're going to see that it says magnetostatic. For this simulation, we're going to need it to be transient. So you're going to right click Maxwell 2D Design, and then go to Solution Type, and then switch it to transient. Next, you're going to right click Maxwell 2D and then select Design Settings. And then you're going to go to Model Depth and change that to 40 millimeters. And then make sure you're clicking Save throughout so that you don't lose any data. Now, if you hold Control and then left click on objects, it'll select both of them, and you can modify both of their properties. So I selected both of the steel portions of the motor, and then if you right click, you can click select material, and then you can search steel and then select steel 1010. That should be good enough for the purposes of this assignment. And here I'm just going ahead and selecting the stator iron and rotor iron and just naming them individually. So now we've got the two steel objects in our model. Here you can see that the winding is one object, both sides. We don't want that, so you're going to want to select the copper pairs. And you can select more than once at a time using Control, and then go right click, edit, Boolean, and then separate bodies. So just make sure when you select those little rectangles that represent the cross section of the motor windings that they're not like paired together when you select them. Make sure they're individual objects. Okay. Next, I'm going ahead and selecting all the copper objects that represent the windings. So if you click the top one and then hold Shift and click the bottom object, it'll select the whole group there. And then once you have all the groups selected, you can see what I just did was I right clicked and then clicked Assign Material and then chose copper from the search bar. And after that, I just decided to change the color so that you can tell the difference between the copper objects and the steel objects. Now we're going to go ahead and define the excitations for the windings. So go ahead and right click excitations and then select add winding. And then here this first winding is going to be stator DC winding is what I called it. and I just chose an arbitrary value, 10 amps. And after that, we're going to add the 3 phases of the rotor. So also make sure you select stranded. So I went ahead and named them all U, V, and W for the 3 phases of the rotor. So right-click excitations, left-click add winding, right-click stranded, and then name it. Now we're going to define which direction the current is flowing in these windings. So for the stator, it's just going to be a direct current that is going to create 2 poles that just stay static. So the top stator, if you use the right-hand rule, if we want that to be the north pole, then we want the electric field lines to be pointing down. So the right copper is going to have to be pointing out of the screen. And here you can see that the arrow is pointing out. So you can select the object and then right-click stator, DC winding, and then click add coil, and then you can name it. This one would be DC north in, and in just means into the screen, which is negative in the polarity. Now you're going to have to define the DC windings on the bottom side. So the right rectangle is going to be the same as the right rectangle on the top, because we want the field lines just pointing from the top straight down. So I accidentally messed up here, and I accidentally made it DC south out instead of DC. I accidentally made it DC south in instead of DC south out, so I changed that. And the bottom left one should be DC south in. And for all of these, make sure you change the number of conductors to 10. And make sure you're saving throughout. Next, we're going to define the windings on the rotor, which has a more complicated pattern than the windings on the stator. So here you can see a 6-slot 2-pole motor, and the winding pattern will have the phases U, V, W, and it'll go in, out, out, in, out, out, if you go around looking at the cross section. So we're going to replicate that here in Ansys. So first we're going to select the U phase. We're going to call it U1 in, and we're going to make it negative because in is pointing into the screen, and just set the number of conductors to 10. Then again, left click the object, right click U, add coil, and then this next one is going to be U1 out. Number of conductors 10, positive. And on to the next one. Now this is the V phase. So you can see the U phase goes in, out. So then the next V phase pole is going to go out, in. So in, out, out, So this will be V1 out. In, out, out, and then in. So left click the object, right click V, add coil, V1 in to the screen is negative. So that V phase was out in, so then the first on this next W phase is going to be in as well. So select the object, assign coil, W1 out. So then we're going to just keep following this pattern around. So in, out, in, out. So then this is going to be U2 out. So U2 out, then as we keep going counterclockwise, I assigned U2 in, and then we're going to go next to V2, and that's going to be V2 in. So V2 in, and then it's going to be V2 out. Assign coil. W2 out, and then W2 in. Then once you complete the counterclockwise cycle, you'll see that this last one is W2 in, and it's right next to the first one, which was V1 in. So the pattern's consistent. All right, next you're going to select this circle. So we're going to create some regions here. And then if you drag it to the edge of the stator, you can create a circle that's the same radius as the stator. And I'm going to title it outer region. And I'm going to select the color as red, and then the transparency, I'm just going to set it completely transparent. All right, next we're going to make the inner region. So we're going to go to the edge of the rotor here, call it inner region. And then when you make these circles, it'll automatically set it to vacuum. So that's what we want. But if it doesn't, just remember you can select the object and then right click, assign material, and then search vacuum. So then we're going to make this third region called the band. This is it's called the band, and it's the region that rotates in the simulation. So we're going to put the band anywhere in between that edge of the stator and the rotor. So I put it at 49.5 millimeters in radius, I believe. I'm not sure. Then we're going to make it red and make it transparent. So now we're gonna want a 0 vector potential boundary. So go to the select tab there, and instead of selecting objects, you're gonna wanna click select and then choose edge. And then you can choose the outer edge of the outer region with a left click, and then go over to boundaries. And you're gonna wanna right click, left click assign, and then left click vector potential. And then in there, it'll just be set to 0, and that's what we want. So hit OK. And then save. So now we're gonna select the band, left click that, and then go over to model, right click model, left click solution, motion step, and then assign band. And then you're gonna wanna choose motion type rotation, and then you're gonna click mechanical, and you're gonna change the angular velocity, and you're gonna just write, you can write RPM, or you can write n synchronous, or whatever variable you want. This will just be the angular velocity of the rotor. And I basically decided to choose RPM just because it is measured in RPM, so it just makes more sense to me. So then when you hit enter, it's gonna pop up this screen, and you can just hit OK, and then we'll edit it by going to Maxwell 2D, and then right click that and go to design properties. And then here you can see that it sets it as angular speed, and we're going to want to create a new variable that the angular speed depends on. So click add, and then call this variable electric frequency. I just wrote elect freak. And the unit type, you're going to want it to be frequency. And then the units, you're going to want to select hertz. And then the value of this can just be an arbitrary number. I just wrote 200. And then the RPM, from the equation we've learned in class, the rotational speed and RPM of the rotor is proportional to the electric frequency. So in the value, you're going to write elect freak times 120 over 2, because there's only 2 poles. Now you're going to see it actually took the units away from that, so you're going to want to click on it and then hit edit, and then go back, and then for unit type, click angular speed, and then units, make sure you select RPM and hit OK. And then hit apply. Just make sure it looks like this, where it says unit RPM and unit hertz. Hit OK. So here, if you select motion setup and moving, you can see it highlights all the objects that should be moving in the simulation. Next, we're gonna want to define the mesh settings. So you can right click copper and then hit select all, and then right click mesh, assign mesh operations on selection, then length based. And then I'm gonna use 1 millimeter, because that will ensure that the mesh is fine enough for the simulation to be accurate. Sometimes you're gonna have to play around with this so that the mesh builds properly, and do the same thing for the iron, and you can just put 5 millimeters because they're larger objects. And then we're gonna want to create the analysis. So we have the motion setup, we have the vector potential, we have the excitations. Next, you want to go to analysis, right click analysis, add solution step. And then I'm just going to call this 2 electrical cycles. So for 2 electrical cycles, it should be the inverse of the electrical frequency, right? So we're going to want to do, for the stop time, that'll be the total time that it simulates over. 2 divided by elect-freq, which is the electric frequency. And then the time step, you can do 2 over electric frequency divided by 100. So that'll be 2 cycles, and then it'll take data at 100 points within that cycle. Now you're going to want to save it, and that's all we need to do here in the student edition, and we're going to need to move it over to the virtual browser through Cal Poly. So go to your portal, go to the bottom, Software Hub. You should know how to do this from the pre-lab, so you can go over to Electronics Desktop and click the blue folder, Temporary Files, Upload Files, and then find wherever you put the project we were just working on. Open, and then it should put it in the temporary files, and then on the virtual desktop, go to the Open tab, this PC, and then the motor you just imported. And now here we have it all set up already. I'm going to go ahead and full screen it so that you can see better. And then hit the little plus to expand the project. Hit the little plus on Maxwell 2D Design. And you can see that all the stuff from the project has been imported. So expand the analysis, right-click to electrical cycles, and then left-click Analyze to run the simulation. So this will take a little bit. I'll probably just cut it in post. Alright, so that took about like a minute, and that's because we had a pretty fine mesh and a lot of solution steps. So now to see the results, what we want to see is the back EMF of the spinning rotor. So you're going to want to right click results, left click transient report, left click rectangular plot. And then in here, you're going to want to click winding, scroll down, and then select induced voltage, then hold control. And you can select U, V, and W at the same time, then click new report, and this is what you should end up with. So now we're basically done. And with this, you can also export it to like Excel if you need to. And for the assignment, I'd like you to just submit a screenshot of this in Ansys and submit your exported file. So if you right click on winding plot 1 and then go to export, then you can name it whatever you want. It should save it to the temporary files on the virtual desktop. So hit save, and then I'm going to exit full screen, and then my files, temporary files, and then if you just click on the CSV file, it should put it in your downloads. And that's what I'd like you to submit to Canvas along with a screenshot of the graph in Ansys. Here, I'm just showing you how I plotted it in Excel. But you just need to send me the screenshot of Ansys and this CSV file.